Good morning, Year 11s, or it's actually good afternoon by 1 minute. Hi, so guys, we're going to be finishing off paper 1 review of the 2015 regional. That's what we're going to be doing. I'm just fiddling around with my other laptop, reducing the quality so it doesn't hog my bandwidth. I'm just going to turn off the TV for 1 second. Hang on. I won't even turn it off so much as mute it. Right. Okay, guys. So let's crack on. Let's crack on with paper 1. We're going to finish this off today. We're more than halfway through it. Obviously, the purpose of this is just to make sure that you guys have got loads of practice. If and when we go back to school, you guys will have a mock to sit. The mock's been written, or is being written by all of the chemistry teachers in BSKL, so we'll be collaborating on it. And I just want to make sure that you guys have had all the practice that you can over Easter. Okay, so let's just jump straight in. So let's go for that one, hide share, and then go straight to here. Okay, so this is where we left off. We finished part 1, looking at an empirical formula, and now we're dropping straight into bonding, which is quite nice. Okay, so now this question for me is relatively famous. I remember this paper being done. The reason being because neodymium made an appearance. And it says neodymium is a metal used in powerful magnets. One stage in the extraction of neodymium from its ore is to heat neodymium fluoride with calcium. Right, so what that tells us is that calcium is more reactive than neodymium. But the reason why this question is so special is because a lot of my students came out of the exam feeling very upset about it. And the reason was, in fact, I'm just going to do it this way rather than, there we go. The reason why they were upset is because this is the GCSE periodic table you're given in the exam. This one's directly from your scheme of work. And what you'll notice is the bottom part of the table is missing. Yeah, there is another section in the periodic table down here. And the problem is neodymium sits around about this kind of position here. It sits kind of below meitnerium around this area. And the students were looking for it and they couldn't find it. And that is an absolute nightmare. If you look at the A-level periodic table, of course, has the F block. So it spits out neodymium. Oh, okay, it's more like underneath bohrium. So there we go. And so that was an absolute nightmare. That it freaked an awful lot of the students out. They did not like the fact that they hadn't given them a periodic table with all the elements on it. They were very upset by it. But you didn't actually really need it. But this was a higher level question. I mean, that immediately is going to cause issues. But first question is balance the equation. So 1 neodymium, 1 fluoride, 2 fluoride. Common denominator is 6. So let's do that. Now we've made a change. Go back to the beginning. 2 neodymiums, 2 neodymiums. Next one, 3 calciums, 3 calciums, and you're done. So there's the first one. Not too tough, not too difficult. I've seen harder ones at GCSE. At one point in the extraction, the temperature of the reaction mixture is 1,100 Celsius. Which 2 solids are solids at this temperature? So who has a melting point above it? Those guys. And notice they've given you a nice big space. It says which 2, but you're just going to give the full name of this. So calcium fluoride and neodymium fluoride. Neodymium fluoride as well. And of course, you're probably going to know I've spelt it badly. Fluorine's funny, the O and the I, fluoride. Next, suggest the most likely type of bonding present in neodymium fluoride. It's going to be ionic. And that, of course, is simply metal, non-metal. We learned that rule at GCSE. That rule, by the way, is not lost at A-level. It is a great rule, but there are exceptions to it. So don't ever lose that rule. It's a great rule. If someone gave me a random compound and asked me if it was ionic or covalent, I'd run that rule. Neodymium reacts with oxygen to form neodymium oxide, suggest a formula. That was hard, and they all wanted the table for this one. And the way that you got this was from here. So neodymium fluoride, so they've asked us to predict neodymium NDO, question mark. They want us to predict him. What are the numbers? And what we know is that it is NDF3. What that tells us, we know that F is always 1 minus from the periodic table. And since there are 3 of them, that means there are going to be times 3. That means there is 3 minuses in total. What that means is neodymium must be bringing +3. So neodymium is a +3 oxidation state. So it's the same as aluminium. So what that means is we're then going to get ND3 plus, O2 minus, good old X factor crossing down, even though I don't really like it, ND2O3. And that was hard, that there was a level 9. That was a love 9. And they're very, very rare, that was really stretch and challenge. I'd never seen them do it on a GCSE paper before until this exam paper. I'd never seen them do it. The concept of being able to dismantle another compound to work out the charge stroke oxidation state of a metal, that's hard, folks. It's really grade C at A level, just letting you know. Right, next, explain. Okay, so the diagram shows particles in neodymium. Sorry about that. Particles in neodymium, and it says it is malleable and a good conductor of electricity. So we've got 2 things that we need to explain. So we're going to say neodymium is malleable due to its atoms forming nice organized layers. Nice organized layers, and those layers can slide. Those layers can slide. Cool, so we've got the first 2 marks. We've got they're in layers and it can slide. We then need to say neodymium is a good conductor due to it having a C of delocalized, that's going to be a mark, a sea of delocalized electrons that can flow, underline, that's the key word, flow through the structure. I like it. Done. 4 marks. Next. Okay, nice bit of internal calorimetry. So they're doing an acid-base reaction. So they're reacting hydrochloric acid with sodium hydroxide, and they're going to measure the temperature change. It's probably going to be exothermic. Well, it will be. I know it actually will be. So we've got to remember to flip that sign at the end when we get there. What is the advantage of using a polystyrene cup rather than a glass beaker? Polystyrene cup gives better insulation. Polystyrene cup provides insulation. So less heat lost to surroundings. So we're going to get surroundings. So more accurate delta H, more accurate measure of heat energy produced. I like it. They're probably just going to want it provides insulation. I just don't trust them. Students, okay, some students, especially boys, have a bad habit of wanting to write as little as possible, and they'll just go, insulation! They'll just give one word. You're going to lose it, folks. The reason why I'm doing that is I'm expecting the fact that it's going to provide insulation is probably going to be the mark, but I'm very aware that the question's a bit ambiguous, and for 1 mark, they could be looking for you to say, therefore, there's going to be less heat loss. What is the advantage to it? You're going to lose less heat. And so I just don't trust it. And also, it makes the measurement more accurate. So I'm giving 3 good, solid reasons for this being better, but I'm not sure which one's going to be the mark. We'll look when we mark it. Right, we know this trap, folks. Everybody knows this trap. So number 1, it says after first. So this is the first one we need to take. So we're reading this from bottom up. So 15, 16, 17, 18, 19, 19.2, 19.4 is going to be my after, 19.4. The next one is 15.2, 0.2, 0.4, 0.6, 0.8, and it's in the gap. Yeah, so that's going to be 15.9 is what that's going to be. 15.9. They want us to do the maths on the temperature change. So I'm going to do 19.4. 19.4 minus 15.9 gives me 3.5 degree temperature change, temperature rise. I like it. Okay. At this point, I feel like I ought to mark it. Blimey, I've suddenly realized I haven't actually got it open. So let's see if I can track this down fairly briskly. That one. There we go. I feel like I just want to quickly go through it and just check that. I'm partly because I want to see about that, the advantage. As I said, big assumption it's going to be insulation, but it would be nice. Oh, I've just done 2016. Shouldn't do that. Clicked on the wrong one. It's thinking about it, folks. There we go. There we go. 2015 regional. Let's go all the way down to where we're up to. I feel like I may have gone too far. I've gone too far. Question 7. Oh, have I clicked on the wrong one here? This is question number 9. So let's see what that gives us. Question number 9, green. Ah, I don't think I've clicked the right paper. What paper is this? This is the 2015 May. Which one's this paper? Have I gone and made a silly mistake? May 2016. Ugh, I've already done the 15. Ugh. So let's close that one. 2016. Oh yeah, we keysted 2. I'm an idiot. Eek. Oh, laptop is really irritating me. Right, let's go down to our question. Where are we up to? Polystyrene cup, that's where we wanted, is an insulator, reduces heat loss. There we go. There we go, and I like it, 3.5, we're on a roll. I'm just going to check the others while we're there. Delocalized electrons can flow, slip and slide. They're in layers. There's my balancing ionic, and there's my formula. I like it. Very reasonable so far. Right, let's go right back to where we were up to. There we go. Okay, so next, plot the graph. Okay, we know these are coming. Yeah, we know they're going to come. So we've got, plot the graphs. We've got sodium hydroxide, volumes, that's 17.6. 15, 16, 17, 18, 19, 20. So that's 17.6 is going to be here. Yeah, I'm going to zoom in on that. 17.6. There we go. And then we've got, try my best to plot these, and then 19.7 for 5. So 5 is 19.7. 19 is there, 0.6, 0.7, there we go. And then 21.6, 21.6, there we go. And then 23.6, 21, 22, 23.6. There we go. And then 23.8, 23.8. There we go. And then 23. It's coming back down now. 23, which is going to be there. And then 30 is 22.2. There we go. I like it. So there's, and then what's it say? So it's draw a straight line of best fit through the first 4 points. I'm going to get my ruler out. Get my ruler out. I love that. I got shown how to do that. I'm going to lose that mark, aren't I? Yeah, that mark I'm definitely going to lose. Realizing that I haven't really got any of the points on that line. There we go. Try that again. That's better. Whoop. Gone right off the page. Lol. And then the next one. And then a line of best fit through the last 3. This is actually a... There we go. Obviously, in the exam, I'd finish them there. That's where I'd finish them. I wouldn't go beyond that. I'll get rid of my ruler. I love the fact that I've got a ruler on this now. Oh, hi, Ira. It's nice to see you. I've just been talking to myself for the last 20 minutes. It's nice to see you. Thanks for coming along. For the points where the lines cross, write down the temperature of the mixture. Right. So there's 24. And that is literally dead. And so 24.2, it's 24.3, isn't it? 24.3. And then the volume of sodium hydroxide, I'm going to get a ruler out for that. Oh, we should go to get a ruler out for that one as well. Yeah. And then, there we go. Cool. So the volume is going to be, that's 11, and that's going to be 11.5. It's 11.45. Wow. 11.45 centimeters cubed. Seems very reasonable. I do want to check that straight away on a mark scheme. See what they allow. Plus or minus. Oh, I like it. So they actually just give you any reading that you've taken off your graph as long as you've shown it. I like that. That's good. Right. Now we've got to run. Oh, there's a ruler on OneNote. Yeah, I know, right? I know. It's up here. It's up there. It's right there. Ruler. It's amazing. Gives me a straight. I love it. Absolutely loving it. In a similar experiment using different acid and alkali, the student recorded these results. Calculate the heat energy change during the reaction. Right, and there says heat energy. So we're just running this Q equals MC delta T. Right, this is all about water. This is what this is all about. So now we need to have the mass of the water. Now, the clever thing about this is we've got acid and alkali. So the two volumes get added together. That's the trick here, folks. So we've got 25 plus 22.7. So I get 47.7 times by 4.2, which is up there, times by a temperature change, given us before and after. So we've got 24.7 minus 18.9. 24.7 minus 18.9 gives me 5.8. They're going to want that somewhere. It's going to be worth a mark, isn't it? Multiplied by 5.8. And I get a heat energy change of 47.7 multiplied by 4.2 multiplied by 5.8. And I get 1,000, assume 1 centimeter is 1, okay, 1,162 joules of energy. I like it. Now, I've actually gone to 4 sig fig there. It's going to be rounded. It's going to be 1160 on the mark scheme, I'm pretty sure. What? Huh. Oh, accept all of my numbers. I like it. Reject. Yeah, that's the only one they'll reject. I like it. That is good. I like it. Stupid. 1200. What the hell? Anyway, sodium thiosulfate. So, by the way, is that it? Doesn't make an awful lot of sense, that. Anyway, that's actually not the heat energy. They're wrong there. They're actually incorrect. That's epic. Heat energy change. They should just say energy change. Yeah. If they want to, I'm not going to even bother. Edit cell. Sodium thiosulfate solution. 20 centimeters cubed conical flask. Yada yada yada. We all did this. It goes cloudy. Right. Calculate the mass of sulfur dioxide formed in this experiment in grams. Okay, so it's just a reacting mass. They've given us concentration. They have given us volume, yeah, of thiosulfate, volume of water, and volume of acid. Oh, that's quite clever, isn't it? And we need to find out sulfur dioxide. So we need to use moles. So the question is, who do I know everything about? 2 of them. Yeah, there's only 2 people here that I can use, and that's these guys. Yeah, the reason being is I need to get to moles. Number of moles equals C times V over 1,000. Yeah, Mr. Duncan, why does it reject the value again? Do you mean why does it reject the 1161.9? I'm assuming that's what you mean. The reason being is that the true value is 1,161. Yeah, 1,061.972. Yeah, that's the full number. Well, if you're going to round to any one of these significant figures, so the first thing they did was they said they wanted you to give you this. That means they've rounded it to 2 sig fig, which is garbage. Yeah, because the 6 is greater than 5, so it rounds up. Yeah, but then I said, do you know what? You could also have 1160. The reason being is that 1 there is smaller than 5, so it gets rounded down to a 0. Agreed? And then if you want to go to the next decimal place, if you want to go to this one, then the problem is that number would, the only thing that would do is round up that number. It would become 1162.0 if you were rounding it to that sig fig. Yeah. And then if you wanted to go to the next one, yeah, if you wanted to go to the next one, that would round that guy, which would then round that guy. Yeah, that's kind of what's happening. So the only number they won't accept is that one because it's been incorrectly rounded. Good question, Ira. Thanks for asking. I read the number wrong. That's my bad. It does happen. Right, back to moles. Number of moles, so concentration, volume. Right, let's run them through. 0.3 multiplied by 20 all over 1,000 because I'm in centimeters cubed. So number of moles equals 6 times 10 to the minus 3. What's the ratio of thiosulfate to sulfur dioxide? It's a 1-to-1. So the ratio, I'm actually going to write it down, you always do, is a 1-to-1. So the moles are the same, therefore, so 6.6 times 10 to the minus 3 moles of SO2. Moles of SO2. Right, now we need to get it to grams. So number of moles is grams over rams. Reorganize to get grams. Bring rams over. Number of moles times by rams gives me grams. So the question is, what does sulfur dioxide weigh? 32 plus 16 times 2, which is 32, so 64. Don't even need a calculator for that one, even though I still would use it. 6 times 10 to the minus 3 multiplied by 32 plus 64. It's going to give me 6 times by 64, and I get 0.384 grams, and I'm done. Good question, that. Great calculation. Can I just point out, by the way, that there is a love 8. The reason why, students say why, because you're using 2 equations in one place. That's a much harder than normal one because you've got to use 2 moles equations in a single question to get to the answer. That's relatively uncommon. Right, the solubility of sulfur dioxide at room temperature is 100 grams per litre. That's awfully convenient. Use this additional information to explain whether any sulfur dioxide escapes from the flask. Right. So the total volume of liquid is 50. Right. So total volume of solution is 50 centimeters cubed. Right. It says here that 100 grams would dissolve in 1,000 centimeters cubed. We can convert dm to cm cubed. We know this. Right, well, hang on a minute. How do you get from 1,000 down to 50? Just divide 1,000 by 50. 1,000 divided by 50 gives me 20. So if I do 1,000 divided by 50 gives me 20. I have 1/20th of that volume. Yeah? So 50, so I'm going to put therefore 50 centimeters cubed is 1/20th of 1 dm cubed. Right. So if that's the case, well, if I can hold 100 grams in 1,000 centimeters cubed, and I have a 20th of that, I can hold a 20th of that mass as well. So I'm going to do 100 divided by 20. So 100 divided by 20 gives me 5. So 5 grams of sulfur dioxide could dissolve in that volume of water. And how many grams did I make? I'm going to see no sulfur dioxide. So 5 grams will dissolve. No gas will escape. No SO2 will escape since less than 5 grams made. Done. Hard question. Great question. Wow, some serious logical process there, guys. That also is a love 8, love 8-9. Most students wouldn't get that. It's just a horrible use of units. Really, really, really clever. Great question. Good stretch and challenge again. The second half of this paper is hard. At what point in the experiment should the student have started the timer? Oh. Before starting her experiment, the student considered the risks of sulfur dioxide, yada, yada, yada. So, a student used this method. Place 20 centimeters of oil on a flask, add 10 tons of hydrochloric acid, place the flask on the piece of paper marked with an X. Time how long it takes for the X can no longer be seen. She should have started the timer when the hydrochloric acid was added. Yeah, when all of the hydrochloric acid was added. Yeah, that's when they should. As soon as that acid goes in, the reaction starts. That's the first time, by the way. So as soon as all HCl has been added. Some students might say, well, can't you say that you could, when she puts it on the X? Well, no. The reason being for that is that the reaction is still going on, even though it's not sitting on the X. And you don't need to really worry about. People would then say, well, hang on a minute, she's done a really bad method. She should have put it on the X and then added the HCl. And I'm like, what difference does it make? For the first 2 minutes, you're not going to see anything happen. It's quite a slow reaction. So in reality, not needed. You can just add it and then place it on top of it. Saves the mess. I want to see a mark scheme, though. Faux sure. Massive SO2 in one. Ooh. Ooh. That's interesting. I got my number right there. Mass in 1 liter. Huh. Times by 50. Oh, there you go. Volume of the solvent. Oh, there you go. Is 50, which would dissolve 1/20th. 5 grams is less than done. Okay, fab. So my method's accepted, but it was the one that they didn't really want. Isn't that fascinating? As the allow immediately after all hydrochloric, ignore when solutions are mixed. Too vague. Yeah. In reality, just so you know, that question's been asked at A-level, this one. It was asked in an A2 paper, and in fact, that's actually the wrong answer. The correct answer is when half of it's been added. Isn't that a nightmare? Because you have to take an average of when it hasn't and when it has. Isn't that bizarre? Horrible that, when it's half added. Anyway, they don't want that though at GCSE. I know, I shouldn't really mention it, I apologize. Result that explained one mistake the student could have made to cause this anomaly. Right, so this mark is the anomaly and it should have been here. It should have been there. Right, so it is less than expected. Agreed? So if it's less than expected, what that means is they've either added too little or the concentration was too low. Yeah, the time, oh, hang on a minute. It's gone, oh, hang on a sec. It's gone way too quick. It's vanished in 40 seconds instead of 70. Oh, that's backwards. Isn't that horrible? Explain one mistake the student could have made. She stopped the clock too early. She thought the cross was gone when it hadn't. But that's 20 seconds. Very unlikely. She's put in a concentration too high. It's gone too quick. Added, what was she changing? Oh, maybe she added too little water. Forgot to add water. Yeah, there's loads of answers, by the way. Forgot to add water. That would work, because if she doesn't add the water, it's not diluted. Therefore, if it's not diluted, it goes quicker, so the reaction goes opaque quicker than expected. She could have forgot to add the water, added too higher concentration of somebody. You'd have to probably want to name someone. Concentration of acid. Therefore, the higher concentration means that it's going to go faster and therefore go cloudy more quickly. Yeah, those two are totally acceptable. There are going to be others on the mark scheme. Suggest 2 reasons why the salt are less accurate at high temperature. Isn't that fascinating? What a great... The student repeated the experiment using nitric acid and placed no longer seen and the times calculated, yada, yada, yada. Suggest 2 reasons why it is less accurate at higher temperature. Look how long it takes, folks. Relative rate in per second. So at temperatures, the rate's really high. Number one, her error's going to be higher. That's really hard. This is a hard paper. Oh man, really tough. So number one is your error's higher. Yeah, the faster it goes, the larger your percentage error when it comes to equipment and whatnot. Also, so if it goes so quick, she's not going to stop it on time. Would you agree? If it goes so quick. I don't know how to word that, folks. Ooh, I might have had a question which I don't like. I don't. One's gone too slow, one's gone too quick. I'm going to write what I would put in an exam. Unable to start and stop clock accurately at such high rates. Easy to overshoot with time when opaque appears so quickly. Oh, I feel like I've repeated myself. I might have just been beaten, folks. Timer stopped too early. Oh, have I lost that one as well? Timer stopped too early. Thermometer scale, timer incorrect. Allow miss incorrect recording of temperature and time. Wow. Timer stopped too late. That's stupid. I disagree. 19.5? What did I have? Oh, have I missed? I missed a question. See, it's so easily done. Use the graph to find a value of x. No longer should be seen at 35. Yeah, 19.5. Easily missed. Blimey. Oh, no. It's time. Eek. That's in seconds. Mr. Duncan, is this the same paper set that you were going through in the previous lives? What? Yes, I've gone through, this is my third paper. This is the one that I did yesterday. I just made a right mess of that. Oh, no, hang on a second. I made a mess of the previous one. I disagree. I feel like there's more that they should allow here. I want to check why they won't accept my answer. Forgot to add the water. Followed the method. Oh, there's no water. Oops. Oh, hang on. There you go. Oof. Made a mess of that. Times are very short. Heat loss greater. More collision. Okay, so M1 and M2. Except heat loss occurs more quickly. Difficult to maintain a higher temperature. Oh, fair enough. Except reaction happens too quickly. Ignore reaction is quicker. Hard to measure rate. Allow human reaction times become significant. Shorter times between greatest percentage error. There you go. There's my error one. Heat loss greater. Right. So I definitely would have lost that one. The second one, that's hard, that. So the second one, I now need to make, I got that one. That one's correct, but this one's wrong. I'm going to make a correction. Yeah, because this particular practical comes up so frequently. I definitely want to have this on my mind. So number 2 should have been at high temperatures, at high temps, heat loss, at high temps, heat loss will be great. Will be great. So won't maintain test temperature, test temp. It'll cool down. That makes total sense. What a great question. Even stumped me. Next, the student wrote this explanation for the shape of the graph. If the temperature increases, the rate of reaction increases. This is because there are more frequent collisions between the particle and reactants. Use particle to explain another more important reason why. Oh, right. So this is kick-ass. But the great thing is she's done one of the points for us. So all she has done is the increased rate. There are more frequent collisions. She has just done collision frequency. That's it. She hasn't done the other one. Yeah. So we need to say particles. This is temperature. Particles have more kinetic energy. You don't actually need the word kinetic, just so you know, but it's nice to put it there. It's good chemistry. Have more kinetic energy. More particles have the activation energy. So more successful collisions. So more successful. I like that question. That's quite nice. Successful collisions. Isn't that lovely? They're actually just taking out a section of kick-ass and making us run the other 3. Like it. Another student uses the same reaction to investigate the effects of changing concentration. Give 3 variables that the student must control in this investigation to obtain valid results. Right. So she's investigating concentration. She will obviously need to control. I shouldn't be writing in green. I'm going to switch back to black. Control temperature, obviously. Control temperature. We're also going to need to control the volume of sodium thiosulfate, of sodium thio. And you're also going to need, now you can't say control the concentration because that's what they're changing, but we do need to control the concentration and volume and vol of hydrochloric acid of HCl. Done. Next. Okay, so they're giving us a lovely train. So question number 1, balance the equation. One carbon, by the way, do you notice it's incomplete? Yeah, one carbon, 4 hydrogens. 4 hydrogens. Oh, no. Easy miss. Blimey. I've gone and opened up loads and loads of... Just gone and... I did not just scream like a girl. Oops. Oopsie. There we go. So, one carbon. Yeah. 6 hydrogens. 6 hydrogens. Easy miss. 1 oxygen. 1 oxygen. Is that literally it? Just a 3. Is that it? 1, 1, 1. It is, amazingly. Go figure. I'm still checking it. Yeah, it's good. The reaction assuming that the reaction reaches equilibrium, explain what happens to the yield of hydrogen if it's carried out at a higher pressure. Right, so we're running coughs. Yeah, so knowledge. Right, so at higher pressure means more particles per unit space. Unit space. Next, oppose. If we raise the pressure, the equilibrium will reduce pressure. Do you know that's one of the most lost marks in the whole of chemistry, from GCSE all the way up to A level? No one ever says it properly to get the mark. We raise the pressure, the equilibrium will reduce the pressure. The O stands for oppose, if you don't know. Yeah, next, favor. How will it reduce pressure? Yeah, it's going to favor something. Favor, the equilibrium will favor the side with less gas. There are, oh, hang on a second. Assuming that the reaction, explain what happens to the yield if the reaction is carried out at a higher temperature but the same pressure. Favor the side with less gas. Right, guys, have you noticed? It's the same. 1 and 1, 1 and 1. 2 on each side. Favor side with less gas. Both sides have 2 moles. Have 2 moles of gas. No change to yield. No shift. No shift. No yield change. Clever question. Next, assuming that the reaction reaches equilibrium, explain what happens to the yield of hydrogen if it's carried at a higher temperature. Wow, 2 coughs in a row. Wow, that's a nice 4 marks. Yeah, if you know how to run coughs, that is. Just by the way, then you just delete this, you see, and just bullet point it like that in your real exam. Yeah, I'd actually put coughs in the margin. Yeah, can't mark it then. Yeah, so knowledge. So the forward reaction. I've suddenly realized I've made a mistake. I've done the wrong answer. Oh, I made a mistake again. It's come out in the wash. That first one is wrong. I've given the rates answer. Knowledge for equilibrium. 2 moles of gas. Moles of gas on either side. On either side of equation. It came out in the wash, but I chose that I do need to practice, just like everybody else. Yeah. We raise the pressure, we're trying to reduce pressure. Favor the side with less gas. Both sides have 2 moles, no shift, no yield change. That's better. Right, coughs, knowledge, temperature. So what's it told me? There's the knowledge. Forward reaction is exothermic. The forward reaction is exothermic. Exothermic. Oppose, if we raise pressure, no, temperature. Sorry guys, my phone's gonna ring again. If we raise temperature,
yes, thank you.
If we raise temperature, the equilibrium reduces temperature. Reduces temperature. I'm going to be good as if I'm in an exam. Reduces temperature by favoring side. Favoring. Oh, hang on. No. Made a mistake. Yeah. Oh. Okay. By favor, what are you going to do? It's trying to reduce it. Yeah, that's what the equilibrium's trying to do. The equilibrium reduces temp. Favor endo by favoring endo reaction. Endothermic, can't just write endo. Endothermic reaction, which is the backward one. So it's going to shift left to right, but we're going to go backwards. We're going to shift right to left. Right to left, yield decrease. Yield decrease. My hand is pressing all of the buttons. Next, how are we doing on the paper? Can't have that much left. Still got quite a lot. Let's continue. Complete the profile by showing products of the reactants and the enthalpy change. Okay, well, just will go all the way back then. So hang on a minute. How bizarre. Complete the profile by showing the products of the reaction. Okay, so products of the reaction. I'm just looking for the equation. I've scribbled all over it. There we go. Isn't that fascinating? They've gone backwards. So have they? No, CO and water go into CO2 and hydrogen. Okay. CO2 and hydrogen. That's really weird. Complete by showing the reactants. It's really strange because you think that that's been set in the middle, but I don't really like it. Is that endothermic? Is it? No, it's not. How strange. That reaction from this way to this way. Guys, it's a trap. This way to this way. Yeah, there to there is exothermic. That graph says endothermic. This is incorrect. This is the transition point. What? CO2 and hydrogen. How bizarre. That's really mean, folks. And the enthalpy change, 2 marks. There's the enthalpy change. Delta H. Blimey, what a mess that was. I had to go and check that. Seemed everyone's just gonna love them on top. Talk about throwing it away. Oh, it's a mess. Oh, you'd lose 2. You'd definitely lose 2. That's a nightmare. The reaction 2 is carried out using an iron oxide catalyst. State the effect, if any, on the catalyst of the enthalpy change. No change. No change. Now, just to explain why there's no change with a catalyst, yeah, it does need explaining. So here's your original line. Yeah, and we know that the heat energy change is that gap there, because this here is energy, that there is energy, and this is start and end. Well, if it starts at 5, yeah, and ends at 1, then the difference is 4. That's the activation energy. But that is the heat energy change of the reaction. Well, if you add a catalyst, how does the graph change? It's still at 5 and still at 1. You've just reduced the activation energy. That's all. One for me? Yeah. So the energy gap is still the same. It's still 4. Yeah, delta H is the same. Cool. So it makes no difference that the catalyst just reduces the height of the hump. Yeah, there's the catalyst. It's still got the same heat energy change. So explain how a catalyst increases the rate. We know this question, folks, and we know it well. Yeah, this is not what a catalyst is. What is a catalyst? A substance that increases the rate of reaction itself not used up. How does a catalyst function? A catalyst provides an alternative route of reaction with a lower activation energy. So more particles now have activation energy. Just gonna leave it at that for now. I want to check that stupid graph on the mark scheme. Temperature, volume, yada, yada, yada. No effect. I like it. Stupid graph. There's my graph. Don't like that graph. Low of activation energy. We're done. There we go. Next, explain which of these is a redox reaction. Ooh. Starts at 0, ends at -3 and +1. Technically, number 1's redox. That's -3, -2, +1. Oh, that's redox 2. That's awkward. It's not -2, it's +2. That's awkward. And the oxygen's going from 0 to... Oh, which of these two is? That's +1, that's +1 for hydrogen. The oxygen is 0, but then is -2 and -2. So the oxygen is being reduced. Oxygen is going from oxy state 0 to oxy -2. And then the nitrogen is going from oxy state -3 to oxidation state +2. That's really hard, this, folks. That's a level 9. Most students wouldn't get it. The other one is an addition reaction. No changes in charge anywhere. Same with the bottom one. That's a neutralization. That's an acid base. There's a base and there's an acid. So the reactions 3 and 4 are both redox. And explain which two of our redox reactions. So reaction 3 and 4 are redox due to loss and gain of electrons. That's an awful lot of words, really, for 2 marks. Ugh. Oh, redox. Okay. I'm going to do it. Reaction 3 is redox due to nitrogen's gone from that to a -3, gaining electrons, due to nitrogen gaining electrons and hydrogen losing electrons, hydrogen losing. I'll do it properly in an exam, by the way. I'm just realizing I don't want to make this longer by having to write all this. Reaction 4 is redox because nitrogen is losing electrons and oxygen is gaining electrons. Ugh, what a waffle. What a vile question. It's really hard. Reaction 3, there was gain of hydrogen. Reaction 4, there was gain of oxygen. All right. Except decrease in oxidation state. Ignore references to loss or gain of electrons. Horrible. Manufacturers produce a batch of 34 kilograms of ammonia. Calculate the maximum mass of ammonium nitrate that can be made. Right, so they're looking at reaction 6. So 34 kilos. So NH3 plus HNO3 goes to ammonium nitrate, which is fertilizer. So they've given us 34 kilograms of ammonia. What's the maximum mass of ammonium nitrate? So number of moles. Step 1, get to moles, grams over rams. So over ammonia, which is 14 plus 3, 17. 34, I shouldn't do it. Convert to grams, 34,000. 34,000 divided by 17 gives me 2,000 moles, right? It's a 1-to-1, the ratio is 1-to-1, because just to show you 1, 1, and 1. Yeah, so from here to here, it's a 1-to-1. So I'm going to get 2,000 moles of that as well, right? How much does this now weigh? So nitrogen is 14 plus 4 plus 14 plus 16 times 3. 14 plus 4 plus 14 plus 16 times 3 gives me 80. It weighs 80. So I'm going to go number of moles is gram, reorganize it, bring rams over there. So 2,000 times by 80. 80 times by 2,000. And I get, convert to kilograms divided by 1,000. I get 160 kilograms. That's my answer. 160 kgs. You could have left it in grams if you wanted. Next. Right. I think this is the last question, folks. We're nearly there. It's taken an hour to do it. The last few questions have been tough. 3 of the fractions obtained from fractional distillation are fuel gas. Identify which of these fractions has the darkest color. Ooh, fuel oil. That's tricky. You've just got to know them in order. Gas, natural gas, petrol, naphtha, kerosene, diesel, fuel oil. God, darkest fuel oil. That's so mean. Identify which of these fractions has the highest boiling point. Fuel oil. Identify which of these fractions contains molecules with the fewest carbons. Shortest one. Gasoline. Gasoline. Isn't it hard? This is hard, folks. This was a hard year. Cracking involves heating some of the fractions to above 650. Name the catalyst used for cracking. Zeolite. Next, finish the equation. Oh, 2 molecules of an alkene. So the difference is 8. So I need 2 for C4H8. Double it and add 2. Double it. CNH2N to get the alkene. Clever that. And you need 2 molecules. That's really clever. Yeah, really clever. Give 3 reasons why cracking is carried out. Supply is exceeded by demand. By demand. Shorter alkanes burn better. Alkene are valuable since used to make polymers. Wow, now I want to mark that, folks, straight away. Great question. God, it's really tough, this paper. Really tough. Fuel oil, fluoride, gasoline, aluminosilicate. Except zeolites. There you go. Except zeolite. Greatest supply of high demand for short chains. They're lighter, except pet short chains are more useful. I'm looking for more flammable. Where is it? More useful, greater demand. Wow, alkenes used to make polymers. Greater demand, more useful. I feel like that's too vague. Burn better. I'm gonna, okay. Shorter alkanes, more demand. But then what's the point of the other demand one? One of the compounds sometimes present in crude oil has the formula C6H12S. Explain why it's important to remove this compound from fuels. When this is so hard, it's got sulfur, folks. When burnt, it will make SO2, which causes acid rain. It's really hard, this, folks. They really are pushing you on this paper. Really good paper to go through. One compound came from crude oil and monomer polymerization, shown here. Complete the following form from the monomer. That's really sneaky, that. They're being outright nasty here, folks, because this is 2 repeating units, and that's got 3 carbons in it. People are going to want to just put that it's complete. That's so mean. That's the double bond. Yeah? So if we divide this here, 2 repeating units, right? These 2 carbons are there. Yeah? So let's put on what's attached to it. This hydrogen goes there. This hydrogen goes there. This hydrogen goes here. And this section goes down here. It's all a trap. Everything's a trap. Next, repeat the process. Yeah? Because, let's start this again, because this carbon is this one. Let's put on the H's, H there, H there. This carbon is this one. Put on the hydrogen and put on the CH3 again, and we're done. Really mean. Guys, this has been a very long and very challenging paper. That brings us to the end of it. Wowza. Guys, that was really, really tough. And definitely there we go. Right, guys. Hey, Ira. Thanks for hanging around and sticking with me. That's a really tough paper, that one. 2016's paper was challenging, and loads and loads of people struggled with that. I do remember it. It was a horrible paper, and kids came out very upset from it. Definitely worthwhile going through. If you've got any questions on those latter few questions, do let me know. I'm a bit scared to do it. It's tough, but have a go. It's well worthwhile. It's a good paper. Guys, I'll see you soon. I'll see you tomorrow for paper 2.